All right, guys, today we have a bargain table find at Harbor Freight, specifically the Hercules brushless 3-inch cutoff tool. I got this, because it was on sale for that without a battery, so that was pretty cool. And I also had a 12 volt from my ratcheting wrench already, and there's every now and then just a good situation that you need to reach up in somewhere kind of tight and cut something off without the hassle of having to deal with an air hose or something like that. So it initially had this hunk of junk on it. Probably see that or saw that in the video of me cutting off a 1/4 inch stainless steel bolt. So I have zero need for this. So took it off already. Some formed sheet metal, looks like aluminum, most likely. Injection molded housing. Yeah, I don't care because I'm never going to use that thing. So what I really want to talk about is this. Is there a drivetrain in there? Is it just a brushless motor? I've never taken apart something that was batterized and meant to spin high RPM like this. So that's kind of what I'm curious about. And also want to just see the other build quality of it. If you don't know, I am a product development engineer. I've been designing stuff in this same conceptual universe for about 15 years, electromechanical consumer products. So I like taking them apart and seeing how they're made, how well they're made, see if I can see any design details that I've never seen before to help me do better at my job, and hopefully show you guys something interesting from that perspective. So if you're wondering, all it means to be a product design engineer is that I probably know less than you if you actually use these tools for a living or do a skilled trade. And Yeah, that's pretty much all it means. And I know big words. So if you're looking for that type of useless information, then stick around. So from the outside, it's really ergonomic. Like it is. It's almost even more ergonomic to me than a drill, and I don't. Might be just because of narrow and length. So that feels good. The rubber on the outside is excellent, as is, I've noticed with all Hercules brand stuff, the rubber is very grippy and soft. And if you don't know, this is a injection molded housing with it's actually bi-injected with a secondary material. That's where the rubber comes from, and it's manufactured like that, which is pretty cool. It really saves costs as opposed to somebody having to apply this with adhesive onto the plastic after the fact. It's just a mold that has pieces that slide out of the way. First, those metal pieces are there for the plastic to be injected, and then those pieces just slide out of the way a little bit, and the second material is injected in the places that those slides, the cavities that those slides created. So it's a much more complicated tool, but once you make the tool, then it makes parts with two different materials really quickly, on the order of probably less than a minute a piece. So yeah, it's this one has three parts, main housing parts, 1, 2, and then there's a no, this is incorporated into the back part is incorporated into these side pieces, and then it's got a cap that comes off right here. So yeah, without further ado, let's get to that. These are probably I would say these are probably hot forged parts, given the detail. I doubt they're definitely steel. I can't imagine they'd be cast. Yeah, forged is my guess for these components. So these useless things here. Cold formed sheet metal. So die A, die B come together. make the part, then these holes are probably stamped out after the fact. So that's a type of manufacturing process that isn't present on, other types of tools. Okay, there's a locking button that is an injection molded piece of plastic over, you know what, that's probably powder metallurgy. And now that I see, I'm betting that's what these are too, that they are powder. You see, you can kind of, if you look real close, you see those ridges right there. And I think I've seen features like that on other powder and metallurgy parts, and similar right there, right there. So that's my guess on that. That's basically when you want cheap, very hard parts. Powder metallurgy is a great way to go. Not, if you dropped them on something really hard, they might shatter, but that's the downside of powder metallurgy. You don't get toughness, but you do get hardness. So, all right. So there's that thing with. Oh, I forgot to talk about the finish on the outside. I like finishes because it really can make the difference in a product, the appearance. And also the feel. So I tend to um, notice the finish, and their Hercules is imitating, the high end brands with this nice matte finish on here. So on all the parts, and the finish on the inside of the tool isn't too bad either. Typically, that's how you can see cheaply made parts. They really look like crap on the inside that aren't the places that aren't meant to be seen. And right here, we're probably going to see exactly what this piece is made out of and all the other housings, which is PA6 dash glass filled nylon 30%. That's what that stands for. So polyamide, PA stands for polyamide, which is the chemical name for nylon. And nylon 6 is the second most common nylon, second only to 6,6. And the reason you would use 6 over 6,6 is colorability and the finish. The glass, that 30% glass, is great for properties, but it tends to accumulate on the surface, and then your surface finish goes to crap if you with nylon 6,6. So nylon 6 is a little bit more expensive, but you don't tend to have the glass migrating to the surface during the injection molded process, and that means you get a nice clean finish that you can't tell that it has glass in it from the outside. So cool. And there is our beautiful drivetrain. Another unique component I haven't seen is this looks like a dust guard seal around the rotary shaft, no doubt to keep all that little tiny debris that's going to be coming off of this wheel at high RPMs. Another thing I noticed just from that is a really fine screen right there. That is finer than I typically see on a drill, and probably no doubt to help with that increased dust and fine debris load that this tool will be producing. So um, there's a good look at the drivetrain, and as you can see, there is no gearbox. It is just driver, brushless motor driver, brushless motor, cooling fan, shaft, and there's the coupler that lets that button lock the shaft for when you're trying to tighten down the spindle screw. Got a good size ball bearing right there. Really nice ball bearing. Yeah, you tend to need bearings when you have high RPM. The higher RPM your application, then you need ball bearings. And if you have low RPM applications, then you can tend to get away with plain bearings. And that looks like another ball bearing right down there. So this motor construction uses a bunch of little stamped plates that stack on top of each other, which is not uncommon. A very substantial cooling fan there. And yeah, so if you don't know the difference between a brushed and a brushless, basically a brushless uses software and a circuit board to tell the poles of the motor, like which poles to energize at what time. Whereas a brush motor, has a mechanical commutator down in there that does the same thing every time, no matter what RPM, and it can't be programmed. It can only be basically to reduce speed. You just reduce voltage, and with this, you can do something fancy called well, you can pulse width modulate also with brush motor, but you can do it in more unique and direct ways with a driver. Basically, you're the software uh, engineer, the firmware engineer decides exactly how this motor is driven, what amps and voltage it gets, and signal it gets, depending on your inputs and the loads and a whole bunch of other variables that the engineer can choose to utilize. So, all right, well, let's take the rest of it apart. Okay, well, so there is uh, the power battery power management circuit in like regular impact drills. That's typically somewhere down in here, but in this case, it's up here, and that big stamped aluminum piece right there is most likely a heatsink, and you can see there is heatsink. Oop, there we go. Heatsink sticky pads right there that are meant to be thermally conductive from the board to this piece, and then dissipates across the surface area. So, all right. Well, there is the entire electrical assembly minus the battery. This is probably not advised. Might shock myself, but worst that can happen is it's 12 volts. Ooh, ooh. Oh, oh yeah, it's it's supposed to be held here, not by the windings. So yeah, might have broke it. I don't know. So the housing is providing the centering of the support to keep the axle, the rotor center in the stator. In this case, the outside windings are the stator, and the inside is the rotor. So really, all I did, the internal magnets were probably rubbing against the inside of the motor when I did that. So yeah, a good example of what not to do. So let's just disconnect that. Okay. All right. So this is a new kind of piece, a new kind of housing piece that has not been on any other kind of tool that I've taken apart. So it has both, unlike this part, notice it kind of has, an A half and a B half. The B half, or the cavity side is the exterior side, and the core side is the internal side. And this piece has both, internal on side A and internal on side B, and then the external is kind of around like that. So this is definitely a more complicated mold because of directions that things have to come from. So something has to come from this side to make those holes, and something has to come from this side to make those holes. Now they could be just tiny little indents that kind of move out like that, and so the tool, but or in this case, let's see if I can tell where the parting is. So that, I think this edge right here is a parting line. So it comes in. Definitely need to. Yeah, though this is. I mean, this piece doesn't have over molded rubber pieces. So aside from that part of it, just the basic concept of the mold of how many slides it needs and how many moving parts it needs. This is a more complicated part than either of the other two. This one is a good example of just a simple A half B half part that just core, cavity, boom, drops out. That's all you need. So does it say? Yep, there's the same material code right there. See all the great little detail you can put into injection molding parts. That's why it's such a powerful value added manufacturing processes. So let's. Oh, by the way, this X is for. That's what they put on parts when they are in the discount bin, so they know that you can't return them after. I think they give you 3 days on parts from the discount bin just to make, like, if they function when you bought them, basically that's all you get. So and so let's check out this part and winner chicken dinner for whoever guesses what the material is. Polyamide 6 glass 1230. And with thermoplast TPE, thermoplastic elastomer overmold. Lot of great detail. All the routing pieces to keep the wires, the routing features to make the wires go where you want them and not, be in the way when you put the two halves together. All built into the ejection mold. You don't need any extra pieces for that. That's some nice strengthening features. So this is probably a common failure point for a tool like this, because it has the mass of the battery hanging off the end of it. So I'm guessing that's why they added some nice extra little hexagonal extrusions, but they're not just extrusions. They also warp around and follow the contour there and are just offset a little bit. So in injection molding parts, you don't want to increase thickness where you want more strength. You want to increase ribbing. So you have uniform wall thickness everywhere, there, everywhere. And then if you want to increase stiffness, then you add ribs, and it's kind of like increasing the thickness, but it makes for a much more moldable part and much more continuous, homogeneous material properties, which is where you get your strength from. So you don't just want to add a thick piece, then that piece is going to cool at a different rate and have internal stresses in it, and it's not going to have the same material properties as the rest of the part that had uniform wall thickness. So that's one of the kind of design considerations with injection molding. You could say it's a limitation, but really it's just something you have to design around. You can still do what you want to do. You just have to abide by certain rules when you do it. So, and then magically, this is the mirror image of that part. And let's see so this screen looks like it's being held in by a little clip, and that is another thing that I have not seen on lower RPM tools. Typically that screen's just kind of sitting there, if it has one at all. It's just kind of sitting there, and you can tell they went to extra lengths to try and ensure that dust does not get inside the drivetrain of this part. So that so that's an injection molded piece, probably just a simple nylon 6/6 white plastic, and then I can't tell if it's a combined process that, like, they could do an overmold and kind of put that in the tool, but I would imagine it would have real difficulty shutting off, which means keeping the fluid from escaping into all places that you don't want it to go. Injection molds are very high pressure, and it will find any crack or crevice that you let the material will go into it. And that's kind of the point, is basically everywhere that you don't have metal. Designing an injection molding tool is you design it to make the part everywhere there's not metal. And if there's tiny little crevices in between the mating pieces that shut off the part, the two halves, where they border, then the plastic is going to creep in there. So I'm going to say that that's probably a post process to adhere that screen onto there, and then it's just look, yeah, they added these cool little features at zero manufacturing cost, just some design cost to put those features in there. And then it slides like that, and it's nice and tight. Oh, well, I guess when the motor's pushing up on it, it's nice and tight. But yeah, I think that's about it. Let's see if they picked a different material for this piece. No, they still picked nylon 6. That's a trend I'm noticing, that it used to be that the parts that didn't need to have good color or good finish, you notice this part doesn't really have a good finish. It's kind of an orange peel. This is what nylon 6.6 looks like when it's not when normally molded, that you don't get a good finish out of it. But I'm seeing a trend that just probably for ease of not having to have two different kinds of materials laying around the manufacturing plant, or giant hoppers of them, they just use the same base polymer for every part, and then just add colorant depending on which part they're making. And then probably the cost of having the second material is outweighed, or the savings of having the cheaper second material is outweighed by just not having to keep it in stock at all. And the simplicity saves money, in manufacturing and supply chain stuff. So, all right, well, that's about all I can think of that's interesting to me anyway. If you have any questions that I didn't answer, leave them in the comment section down below. If there's anything part you would like included, what tools have you guys used that you think has design flaws that you think it'd be cool for me to take apart and inspect what you think are design flaws, and maybe comment on them or something like that. And always please like, share, subscribe. You got a grandma that's kind of bored. I think she might be up at 3 a.m. too, wanting something interesting. Well, not necessarily interesting, but you get the idea. Just share. That's basically the moral of the story that I'm trying to tell. That helps me the most, organic sharing. But maybe you don't want to help, and that's okay too. But have a good day either way. Thanks, guys. See you later.